Welcome to the third video in our second grade just-in-time session number 1 series. In the third video, we're going to dive into the module that you're teaching the majority of the time in the second 9 weeks. We're going to dive into the priority standards of that module, looking at some data surrounding the TEKS in that module, and we're going to look at some instructional strategies highlighted in that module. As a second grade teacher, you're going to spend most of the second 9 weeks talking about Module 4, which is addition and subtraction within 200 with word problems to 100. I want to begin by highlighting a feature in the Great Minds app that will be very beneficial as you're planning for this new module. If you click on the Great Minds app and class link, once that pulls up, select your grade level, second grade. Select the module. This says Module 1. You would select Module 4. And then it will say Module Resources. You're going to go down and select Module 3 or 4, Preview Video. These videos are amazing. They're only 5 or 6 minutes long, but it would be a really great resource to look at before you start a new module, whether you're doing it as a team in PLCs or if you're doing it individually just to prepare. Each video starts with a segment that covers previous learning. These are skills that vertically align to the skills you are about to teach in the module. So it's what your students should be coming to you understanding, whether that's from a previous grade level or from a previous module. It gives you an idea of where their starting point is. The bulk of the video is spent going over each of the topics in the module, giving you just a bird's eye view of those topics. It tells you what the learning is going to be. It shows you valuable models, tools, and strategies that are highlighted in each topic, and just gives you an overall progression of how the module goes. And finally, there's a segment at the end called Extending the Learning. And this is where you again get a vertical glimpse into where are my second grade students taking this learning, either later in second grade or in a future grade level. So you get that whole vertical alignment piece. In Module 4, there are 3 priority TEKS. 2-4C, solving one-step and multi-step word problems to 1,000, although for now we're only going to 100, using a variety of strategies. 2-4D, generate and solve problem situations for a given mathematical number sentence. And 2-7C, represent and solve addition and subtraction word problems where the unknowns can be in any one of the terms of the problem. To help us with that vertical piece, we're going to go back to first grade and look at where our students are coming to us from. In first grade, there are 4 TEKS that vertically align to the work that you're about to engage in with your second graders. The first one is 1.5D, representing word problems involving addition and subtraction of whole numbers through 20. So they're coming to you in first grade, understanding word problems through 20. You're going to take them through 100 right now, and then through 1,000 later on. So that's a big jump. 1.3B, use objects and vectorial models to solve word problems involving joining and separating and comparing sets within 20. Okay, so the unknown can be in any term. So very similar to our TEK in second grade. They just only did that through 20 in first grade. 1.3E, explain strategies used to solve addition and subtraction problems up to 20. And 1.3D, apply basic fact strategies to add and subtract within 20. All right, to finish out our vertical view, let's see where our second graders are going to take the learning about addition and subtraction in second grade. It's going to build the foundation for these 2 very important TEKS in third grade. 3-4A, solve with fluency 1-step and 2-step problems involving addition and subtraction within 1,000 using strategies. So it's very similar to the TEK that we have in second grade, just with increased rigor. And then 3-5A, represent 1- and 2-step problems involving addition and subtraction of whole numbers to 1,000. So we're solving and we are representing. There wasn't really second grade data as a district that I could look at. I know we have our AimsWeb data, but it wasn't really focused on addition and subtraction beyond basic facts. So I thought rather than doing that, let's look at where our vertical TEKS, those third grade TEKS that we're building the foundation for, let's look and see how our third graders are doing. And it will tell us how important our job is as second grade teachers to establish this foundation. We're going to focus on 3-4A and 3-5A, and we're going to look at the STAR test from last year, the year before, and then the CBA, the curriculum-based assessment they took on addition and subtraction last year. All right, so 3-4A, you'll see on STAR, 54% of our kids got it right. There were 2 questions. Let's take a look at them. The first one said, Tina hikes in the summer, winter, and fall. She records how many hours she spends hiking in the table as shown. How many more hours does Tina hike during the summer and winter combined than in the fall? So really, this could be a second grade question. After we're adding and subtracting and word problems up to 1,000, we could do this in second grade. So why is this so hard? Why did only 57% of our third graders get it correct? Well, that's because it's a 2-step problem. At its core, it's a comparing problem. We're comparing summer and winter combined to fall. So first, we have to realize we're combining summer and winter together. And then we have to subtract fall away. So we have to understand what the 2 steps in that 2-step problem are. The second problem was only 51% of third graders were able to get it correct. Casey bought 2 bags of beads. One bag contained 250 beads. The other bag contained 400 beads. Casey used all but 36 of the total number of beads for an art project. What was the total number of beads that Casey used for the art project? So again, the numbers are not outrageously big. This could have been a second grade problem after we get through Module 5. So why did our kids have such a hard time with it? Well, again, it's a multi-step problem. So essentially, we are looking at the total number of beads that Casey used for the art project. So we have the total number of beads. Part of that are the beads that she used for the art project. The other part are the beads that she had left over. So first we have to get the total number of beads by adding bag 1 and bag 2. So that's a part whole problem where we're missing the whole. And then we have to separate 36 of those beads out to see what's left over. So we have 2 completely different problem structures happening within this one problem, and it's a text entry. All right, same TEAC in STAR the year before. 54% of our students got it correct. Again, it's made up of 2 questions. This first question, almost 76% of our kids got it correct. So a much higher percentage than what we've been looking at. A school had 375 hot dogs to sell during a carnival. After the carnival ended, 83 hot dogs were not sold. How many hot dogs were sold during the carnival? Well, it's only a 1-step problem. It's a part whole problem. We are missing the part. So we know the total number of hot dogs. That total is made up of hot dogs that were sold and hot dogs that were not sold. We know how many were not sold. If we subtract the part we don't know, or the part we know, we're left with the part that we don't know. So it's a 1-step problem, fairly simple structure. The other problem, though, only 32% of our kids got it right. So that's why it averages out to 50-something%. At a weekend bake sale, 295 cookies were sold on Saturday. On Sunday, 88 more cookies were sold than were sold on Saturday. What is the total number of cookies sold on Saturday and Sunday? So initially, it sounds like a pretty simple problem, right? It's just part whole. I'm adding Saturday and Sunday together to get the total. The problem, though, is that it doesn't give me Saturday and Sunday. It gives me Saturday, 295, but on Sunday, it tells me that there were 88 more cookies sold on Sunday than Saturday. So first we have a comparing problem where we have to solve for Sunday, and then we can add the Saturday and Sunday together, my parts, to get the total. Those comparing problems are tricky. So if I can establish which quantity, Saturday or Sunday, is the larger quantity, I can put it in the top. So since it said on Sunday, 88 more cookies were sold, we know Sunday is the larger quantity and Saturday is the smaller quantity. Then I can fill in the numbers that I know. I know for a fact there were 295 cookies sold on Saturday, and I know that there were 88 more than that on Sunday. That's that comparison number. The how many more is the bigger bar than the smaller bar. Once I get my strip diagram labeled, it's pretty easy for me to see. To find Sunday, I'm just going to add them together. Once you know Sunday, then you'd add that to Saturday in order to get the total. But there's a lot going on in that problem. All right, 3-5A, only 42% of our kids got it correct. You can see that we're taking a word problem and representing it on a number line. So our kids need a little bit of work with number lines. And finally, 3-5A and star. We have a word problem and we're asked to represent it in 2 different ways. This was partial credit, so they could get partial credit if they got one of the 2. It wasn't all right or all wrong. If they got none of the correct answers, they weren't able to choose either one of them, they got 0 points. 18% of our kids were not able to select any of the correct representations. 31% of our kids were able to select one or the other, and only 50% of our kids were able to select both. And it turns out that they were looking for an equation and the strip diagram. Okay, so we have 2 issues. We have computation issues, like actually the process of adding and subtracting. Do our students have enough strategies in their toolbox that they can use to calculate the answer? Do they know amongst their tools what the most efficient strategy for them is? And that depends on the strength of the student and the types of numbers that are given in the problem. And it's not always about the standard algorithm, especially in 2nd grade. The other issue we have involves problem solving. Understanding the context of the problem, being able to choose the correct operation or operations, and it's all about understanding the problem structures. Since we're focused on Module 4 is going to focus on computation strategy, so that's what we're going to go over. We have some addition strategies, and we have some subtraction strategies. The addition strategies start with simplifying strategies. Strategies I can manipulate the numbers and make it a problem easy enough to solve in my head, mental math. And then it has strategies and algorithms based on place value. Those strategies and algorithms based on place value go through the concrete, representational, abstract cycle, as we'll go over and talk about. Let's start with simplifying strategies. So in this problem, they're asked to add 38 plus 15. To make it an easier problem to do in their head, they're going to decompose 15 into 2 and 13. They did that because 38 and 2 makes 40. And once I have a multiple of 10 in my head, it's pretty easy to add or subtract from multiples of 10. So 40 plus 11 over 13 makes 53. Here's another example of 2 children who solved the same problem. So we want to be fluid and flexible. Remember that what it means to be good at math, fluid and flexible. They were both solving 58 plus 19. Sal decomposed 19 into 2 and 17. He did that because 58 plus 2 makes 60. Again, that multiple of 10. Adding 17 to it gives me 77. Beth, though, she realized that 19 is really close to 20, so she chose to decompose 58 into 57 and 1, because 19 and 1 makes 20, plus the extra 57 gives me 77. Either way is correct. In this problem, it's another form of simplification. He's taking 24 of his homework problems and adding the 51 that are left over to do. He decided to decompose 51 into 50 plus 1 because adding multiples of 10 is easier. 24 plus 50 is 74, plus the leftover 1 is 75. They used arrow notation to make that thinking visible. So we can use number bonds or we can use arrow notation to make our thinking visible. Now let's talk about strategy and algorithms using place value. So we're going to start concretely with place value discs. When I'm adding, I want to add both. I want to represent both add-ins because I'm going to be joining them together. So in this example, we are adding 26 plus 35. They built 26 and 35 with the place value discs. We look in the ones place. When I push my ones together, I get 11 ones as shown in the second picture. We know that if I take 10 ones, I can regroup them or bundle them for an extra 10 as shown in the third picture, leaving 1 left over. And that gives me a total of 61. So we begin concretely with those place value discs. As we are building the bridge to representational thinking, We want to represent what we're doing with those discs on paper side by side to build that super strong bridge between concrete and representational. So maybe the teacher is building, or maybe the students are building with place value discs and the teacher is drawing the discs. And then it flip-flops to where maybe, as we've done a few, the students are now drawing and the teacher is building. You can still represent that bundling process by circling 10 of the ones and drawing an arrow to a new bundled 10, giving us 61. The teacher is recording the vertical form, which is the standard algorithm, off to the side, each step one at a time, showing what they're doing. So as I am rebundling those 10 ones for a 10, I'm showing that down here. Then we're going to go through representational. We're going to start with the pictures of the place value discs. And we want to move to a more efficient representation, especially as we get into bigger numbers. We're going to use the chip model. So the chip model is just dots because they're faster and easier to draw. But because the value is not labeled, we have to have them on a place value chart. So again, we're just representing both add-ins. We start with the ones, combining our ones. Can we bundle? Yes, we can. If I add 9 plus 3, I get 12. I can circle 10 of them and bundle it for an extra 10. That step is shown right here. Then I look at my tens. I have a total of 6 tens, which is 60. And then I have 1 in the hundreds places, which is 100. So a value of 162. And then finally, we want to get to some of our more abstract representations. We're going to start with the chip model and build a bridge to the expanded algorithm. So in this problem, we're adding 126 plus 35. We did it with our chip model. And then side by side, we want to show what that looks like. So 126 is 100 plus 20 plus 6. And underneath that, we have 30 plus 5. They start in the ones place. 6 plus 5 is 11, and they record that. In the tens place, 20 plus 30 is 50. And then in the hundreds place, we have 100. We know that we can rebundle 10 of these for an extra 10, and that gives us 161 as an answer. We're building that bridge, doing them side by side at the same time so they make sense. Another more abstract form is the what's called totals below, or partial sums. So in this one, we have the chip model off to the side, which you can continue to do. Or for a new problem, we have the standard algorithm. 68 is 60 plus 8. 53 is 50 plus 3. When I add my ones together, I get 11. When I add my tens together, I get 110. Again, realizing that I can bundle 10 of these for another 10, making 120, plus 1 is 121. In the partial sums or totals below, instead of leaving our two partial sums side by side like this, I would record them vertically. So it starts to look like the standard algorithm. In the ones, 8 plus 3 is 11. In the tens, 60 plus 50 is 110. And then when I add my two partial sums together, I get 121. That's called the totals below algorithm. Just a couple quick vocabulary review. So when we're showing the standard algorithm in second grade, it is always, always, always in conjunction with another strategy. Second graders are not expected to master the standard algorithm for addition or subtraction. So in this case, we are matching the vertical form, or the standard algorithm, with the place value discs. And you'll notice, it might be a little strange to you, that when they regroup down here instead of up here, like what we were taught. That's because Bluebonnet realizes that students that are just learning the algorithm often forget that regrouped one up at the top. And so instead, they call it new groups below. They put their new groups underneath because students add going top to bottom. So if I'm adding top to bottom, 2 plus 3 plus 1, I'm a lot less likely to forget that 1 because it's right there with the other 10s that I need to add. All right, so that was a brief overview of all of the addition strategies. Let's go over subtraction strategies. In subtraction, we also have simplifying strategies to make the problems easier to do in our head. And then we have strategies based on algorithms and place values. The first simplifying strategy is called count on. It's also known as think addition. Addition is easier for a lot of our kids. And so if we can teach them that if I'm trying to find 82 minus 27, then I'm really just looking for the difference between those two numbers, like on a number line, how far apart they are. So it doesn't matter if I start at 82 and count backwards, or if I start at 27 and count forwards, I'm looking for the distance between those two numbers. So if they started at 27 and counted up, they might go 27 plus 3 is 30. Now that I have a number that ends in a 0, that multiple of 10, it's easier for me to work with. 30 plus 50 is 80. 80 plus 2 is 82. I added a total of 55 hops. So the distance between those two numbers is 55. My answer is 55. Or students can choose the same thinking. I need to find the distance between 82 and 27, but I'm going to count backwards. So I'm going to start at 82 and count backwards a total of 27. 82 minus 2 is 80. 80 minus 20 is 60. I've subtracted a total of 22 so far. I need to subtract 5 more. 60 minus 5 is 55. And they're using that arrow notation to show their thinking. This is arrow notation too. It's just rounded arrows. Another simplifying strategy is called compensation. So compensation is that idea, again, focusing on the fact that subtraction, if you visualize the two numbers on a number line, it's the distance between the two numbers. And for compensation, if I add the same number to both numbers, I'm shifting that space down the number line, but the distance is staying the same. So in the book, they go over this strategy. They introduce it with a really neat hands-on activity using snap cubes. Make sure you read over that strategy and you model it with your students because it's really important for them to understand why the compensation strategy works. So in the book, it has them take out five yellow snap cubes and 3 red snap cubes. How many snap cubes am I holding? I'm holding 8. Well, how many are in this stick? 5. What's the difference between 8 and 5? Well, if I break off those red ones, the distance or the difference between 8 and 5 are those 3 red cubes. What number sentence could I use to represent the difference between 8 and 5? Well, I could use 8 minus 5 equals 3. Then it has them add 1 green cube to each of those 2 sticks. Has my difference changed? No, I still have the difference of 3. I added a green one to this stick and a green one to this stick. The difference is still 3. What new number sentence can I use to represent the difference between my 2 sticks? Well, now I can say 9 minus 6 is 3. The difference is still 3. I had a teacher who also used actual children and a physical number line in their room to model that I can take a student and put them at 25 and another student and put them at 17, count the difference between them, and then move both people the same distance down the number line. That's me adding the same thing to both numbers, but the distance between the two students stays the same. So when we're modeling it with strip diagrams with larger numbers, we are adding the add-in that we're adding to both of them off to the left. We always do it off to the left because this helps us see that the difference is staying the same. When I add 1 to both numbers, 32 minus 19 becomes 33 minus 20. Because it's a multiple of 10, it's easier to do in my head. All right. Our strategies and algorithms based on place value. We're going to go through that concrete, representational, abstract sequence. We're going to start concretely with place value disks. When we subtract, we only model the first addend because we're going to separate from it. So I'm only going to model 46. And I start by asking, do I have enough ones to take 8 away? I don't, so I'm going to regroup a 10 and unbundle it for 10 ones. So now I have 3 10s and 16 ones, still 46. And now I am going to subtract the 6. But before I do that, I want to make sure I'm building that bridge. After we've done several examples concretely, I can move into drawing the place value disks. When I regroup, I just cross out the 10 and redraw the 10 that I unbundled to get it. And I'm using the vertical form off to the side. Remember the standard algorithm, we're using it in conjunction with another strategy. So I'm showing that I took a 10 away and I regrouped it for 10 ones plus the 6 I already have, give me 16. Now I can cross off the 8 that I needed to take away, and I'm left with 28. Once we've done several examples of drawing the place value discs, we can get a more efficient representation and bridge to the chip model on a place value chart, still being able to show the regrouping process. As we get into larger numbers, I wanted to point out that students are using the chip model, and the book has them draw an hourglass around the number we're starting with. That's because we really want to analyze each of those digits before we subtract to make sure that we have enough. So we do all of our unbundling at the beginning, and we subtract only when there's enough of each place value. So in this one, we only had 6. We had to take 9 away. That's not enough. So I'm going to unbundle a 10 and regroup it for 10 ones. Before I start subtracting, I check my 10s. I have one 10. I need to take away a 10. So I can do that. Then I'm ready to start my subtraction. All right, in the next video, we are going to highlight a brand new resource that will help your kids practice these strategies and help them learn the instructional strategies that you've introduced them to.